Hey everyone, let's dive right into this explainer and explore the fascinating world of rigid motions on a coordinate plane. If you've ever played a video game and wondered how the code perfectly moves a character across the screen without warping them into some unrecognizable blob, well, you are in the exact right place. Today, we're looking closely at two very specific types of geometric movement. Here's our roadmap for today. We'll be covering 1. Defining our transformations, 2. Tracing the translation, 3. Tracing the reflection, 4. Properties and orientation, 5. Reflection versus rotation, and finally 6. A recap and transfer question. All right, part 1. Defining our transformations, the basics of rigid motions. Let's get our terms straight before we start moving things around. So, in geometry, a transformation basically takes points as inputs and gives you new points as outputs. Today, we're zoning in on rigid motions. Think of a translation as just a simple slide. You're just moving a figure from one place to another without turning it at all. A reflection, on the other hand, is a flip. We call them rigid because they move the shape without stretching, shrinking, or warping it in any way. The size and shape are totally locked in. But to actually perform these transformations on a coordinate plane, you must have some very specific intel on hand. Otherwise, you literally won't know where the shape is supposed to go. For a translation, you've got to know exactly how far to slide the objects and in what direction. You know, something like, hey, move this up 3 units and right 2 units. For reflection, you need a highly specific boundary to act as your mirror, which we call the line of reflection. Moving right along to part 2, tracing the translation. The journey begins. Let's introduce our VIP triangle ABC. Check out the original coordinates here. Our mission is to move our figure right 2 units and up 3 units. To pull that off, we literally just take every single x coordinate and add 2, and take every y coordinate and add 3. It's that straightforward. So for point A at 1, 1, we add 2 to the x, getting 3, and add 3 to the y, getting 4. We repeat that exact same arithmetic for points B and C. The entire shape just smoothly slides up and to the right, keeping its exact dimensions perfectly intact. Okay, pause check. Please pause the explainer right here and use what we just learned to calculate the new coordinate for point D. Grab some scratch paper if you need to, and really think about how moving left and down is going to affect those positive and negative values on the grid. All right, let's see how you did. The correct answer is -1, 1. Why? Well, moving left and down means we have to subtract from our original x and y values. Left on the x-axis is negative, and down on the y-axis is negative. So 2 minus 3 gives us -1, and 2 minus 1 gives us +1. Great job if you nailed that. If not, no sweat. Just remember for next time that left and down always means subtraction. Part 3. Tracing the reflection, the next step. Now we're going to take our newly translated triangle and flip it like a pancake. Look at the data change here. When we reflect our triangle across the vertical y-axis, the x-coordinates reverse their signs, but the y-coordinates, they stay exactly the same. Notice how point A prime flips from a +3 completely over to a -3, but its height, that y value of 4, doesn't change one bit. It lands exactly the same distance away on the opposite side, creating this perfect horizontal mirror image. Time for another quick pause check. Look closely at how the numbers changed and try to identify the line of reflection used for point E here. Ask yourself, which coordinate stayed exactly the same, and which one flipped to its opposite? Pause the explainer right now and see if you can figure it out. Did you catch it? The answer is the x-axis. Because the point stayed horizontally fixed at 5, but dropped from a height of +5 all the way down to -5, the mirror doing the flipping had to be the flat horizontal x-axis right in between them. Okay, part 4. Properties and orientation, what changes and what stays. Let's look under the hood and analyze what happened to the internal properties of our triangle. Because translations and reflections are rigid motions, they perfectly preserve the shape. I mean, perfectly. If side AB was 3 units long before the slide and the flip, it is locked in at 3 units long afterwards. If angle A was a perfect 90-degree right angle, it stays exactly 90 degrees. The new shape is entirely congruent to its original self. Now, while both of these motions totally change the position of the shape, orientation is a whole different story. A translation keeps the shape facing the exact same way. The left side stays the left side. But a reflection, that reverses it. Think about looking at text in a mirror or taking a mirror selfie. Left becomes right and right becomes left.
That reversal of orientation is the absolute signature footprint of a reflection.
Moving to part 5, reflection versus rotation, clearing the confusion. People mix these two up all the time, so let's set the record straight before we wrap up. A reflection is a flip across a line that creates a mirror image, whereas a rotation is a turn around a fixed center point that spins the shape without mirroring it. Keep in mind what we just established about orientation. A rotation, no matter how many degrees you turn it, preserves the original orientation. The internal left and right relationships of the shape do not get mirrored, but a reflection explicitly reverses them. So if you're ever confused between the two, just check the orientation. That's your ultimate test. And finally, part 6, recap and transfer question, putting it all together. We've covered a ton of ground today, so let's do a quick recap. By following these simple steps, we didn't just move a shape around. We mathematically proved its fundamental size remained preserved, all while discovering how reflections uniquely flip orientation. We applied specific data to X and Y coordinates, we witnessed how position changes, and we totally locked down the exact definitions of our transformations. I want to leave you with this provocative transfer question to chew on. Based on everything we just learned about orientation, could a single rotation ever perfectly mimic a translation combined with a reflection? Think deeply about what properties a rotation preserves versus what a reflection actually changes. I really hope this explainer helped you visualize these mathematical motions in a whole new way. Thanks for learning with me today.